Thank you to the organizers for inviting me. Great to be here. Yeah, so this morning we heard truly exciting talks about foundation models, these universal machine learning potentials, large language models. Here, going to be discussing much simpler models that help. I took the session title very literally when it said knowledge discovery, so I thought this talk would be fitting for this session. I first want to acknowledge Suryo Linich. All this work was done with him. We had a student, Jock, who is now working at Amazon doing machine learning, and NSF for supporting this research, NSF Adapt, Eager Grant, and then DEMREF is also supporting it. So thank you, Bob, if you're there. And yeah, let's begin. So, I think it's safe to say that most applications of machine learning catalysis are using these large black box models, and for good reason. They can be very accurate. You have this input and then an output. Some of these models are proprietary. Sometimes they're just too complicated to understand the inner coding for a human. So that's what I mean by black box. These may be deep neural nets, Gaussian process regressors. Again, great for making fast and accurate predictions, but not always for understanding. And if the goal is to have a specific hypothesis and you want to ask some specific scientific questions, sometimes there's other models that may be beneficial to use instead. So this idea in the literature, it's been proposed you can kind of bucket these in black box, gray box, glass box as you go from less interpretable to more interpretable. So black box, we've discussed those all morning. You have your input features xi, you have some, if it's regression, maybe you want to predict some target y star. You don't necessarily, it's difficult to distill that knowledge of how the model's making the prediction that it's making. Like Mark was talking about with the LLM, you couldn't say why GPT is doing what it's doing. Gray box methods are sort of post-processing methods, maybe feature importances for random forest. So you have your model, and then you try to distill that knowledge and have some actionable insights come out. Glass box or transparent models are by construction most interpretable. Something about the way they're constructed lets you get explanations out directly, and I'll give you some examples of that. So some common, many of these methods have been used in the field of heterogeneous catalysis. So for gray box methods, maybe global feature importance scores, again, like feature importance for random forest, has been used for CO absorption during CO2 electroreduction. Partial dependence plots show you the marginal contribution of a feature in a model and how that predicts the target output Y. Been used to look at small molecule absorption of oxides. Shapley additive explanations are commonly used. It's a sort of game theoretic metric to look at the features contribution. That's looked at OCM, and I'll show you, I'll mention an example at the really end on alloys that used Shapley. Glassbox methods, I'd say probably symbolic regression is the most commonly used sort of glassbox method used, either from genetic algorithm. There's this lasso, CISO is a common one that's being applied. You basically get these analytical models that then you can then interpret. Of course, they're not perfect. You could have degenerate models that have different features in them. Subgroup discovery, GAMs, I'll tell you more about today. And then you can also think about attacking it from other angles using causal models. Just to give you some high-level highlights. This is not up to date. This is from 2022. This table. So, glassbox models there's not really an all-purpose definition. If you go to different fields, they might tell you something different. You can't really exactly say what does that mean. It could mean different things to different people, but typically they may be sparse, so low dimensional. They can have physical constraints from domain knowledge. They may be theory infused, that language is used. They're often additive because then you know how each term sums up to contribute to the model's output. They may have logical rules in them and or. Simulatable means that a human can internally simulate the reason about its decision-making process. So that's a pretty strong constraint, but those are some things that have been thrown around in the literature. People often say there's a transparency accuracy trade-off. That is true in some cases, but it's not necessarily true if it's the right problem with the right features. Generalized linear models, of course, are really transparent, often not very accurate. Generalized additive models are a pretty good trade-off. It's a sum of nonlinear functions, h, where each function h depends on one feature x, I. And then as you go down to these, maybe a foundation model or universal MLP might be a full complexity model. So I think there's a lot of opportunity for synergy between these two approaches. With the growth of use of these foundation models and MLIPs, you can simulate more data. We talked about Materials project and getting better data sets that then and building new databases that'll be discussed later today is helping with this workflow on the left side. And then when you want to get potentially more insight, you can look at these subsets of data, apply these interpretable ML tools, get more physics-based explanations, and that can synergize. So I think they work well together. So the question is, how can this be used in catalysis? Catalysis is so complicated, we always want to find descriptors that simplify this process. From spot-to-air principle to D-band center to OP band level for metal oxides, this is usually developed with human intuition and some fundamental theories. The question is, can machine learning help in this approach? In 2020, there was a symbolic regression paper for oxygen evolution reaction on perovskite catalysts. They found this octahedra factor divided by the Goldsmith tolerance factor. Mu over T was a descriptor. That has to do with the stability of the oxygen. So it made sense that would correlate with the reactivity of the oxygen. This figure is from that paper cited on this. This schematic is taken from that paper that I cite here. So the question is, can this be used more? So I'm just going to show you an example that we worked on, Suyo and I worked on together using IGAM. I showed you earlier, a lot of these studies look at chemisorption for good reason. It's there's more data available. It's very important for determining the coverage of catalysts. It's known to be a descriptor using traditional linear scaling relations. You compute binding energies, and you can relate that to the turnover frequency in these volcano plots. You can also start to rationalize chemisorption with these geometric electronic structure models, such as D-band model. And this is widely known in the literature. So here's an example that I'll be focusing on here, is looking at alloy and core shell catalysts. Just basically the question is, if you perturb a surface, how does this impact the chemisorption strength? So this is common for, again, alloys and core shells. I'm going to highlight here, but if it's a doped metal oxide or it's any material, you can imagine that these are perturbations when you do something to the surface. And strain and ligand effects are known to be two prominent, not the only effects, but they're prominent effects that affect adsorption. So when you make these catalysts, they can have compressive strain, they can have tensile strain. When you imagine you have a fixed metal surface and you change the sublayer. So imagine in like a core shell, you dope the subsurface. If these ligand atoms or dopant atoms have more orbital overlap or less orbital overlap with the surface atoms, that'll change the adsorption strength. And this can be traditionally recognized with, if you have compressive strain or more orbital overlap between the subsurface atoms with the surface atoms, that's going to make the surface feel more coordinated. So it's going to want to bind things traditionally weaker if it's covalently adsorbed. And this is rationalized by having a widening D-band center, downshifts to maintain constant filling. That will cause the antibonding orbitals of adsorbates to be more filled. Tensile strain would be opposite. You stretching a material, the surface will feel less coordinated. It's going to want to be more reactive. If you think about just, it's feeling its neighbors less. Same if the subsurface is doped with something that's interacting more weakly with the surface, it's going to also feel less coordinated. So it's going to want to bind things stronger typically. This can also be rationalized through these electronic structure theory models, which is the electronic states will become more discrete. So it narrows, it upshifts in energy. That'll cause the antibonding orbitals of the adsorbate to be less filled, so it would bind stronger in the traditional thinking. Hong Liang and Suyo, they've looked at these types of systems extensively, studying back more than a decade ago. And, it's qualitatively accurate, not quantitative. But sometimes you get complete opposite trend, right? And this is kind of what stemmed the initial question of could interpretable ML help in this question? So OH binding on platinum and palladium have the opposite trend. So here I'll show you how Interpret ML can shed some insight on why you might have these opposite trends and is it extendable. So these generalized additive models, what I'll talk about, very simple compared to all the models that you all have discussed this morning. But that's part of the beauty, is it's just a sum of functions that are an ensemble of decision trees. So function F1 just depends on feature X1, function F2 depends on just feature X2, function F of n just depends on feature X of n. And then because each of these only depends on one feature, you can just plot how y depends on X1, how target y depends on X2, etc. And you can see these shapes. This was came out in 2012. So unlike foundation models, you don't need a lot of data to apply these methods. Just looked at different host metals with different ligand metals in the subsurface, looked at different adsorbates. I'll show you O, OH, S, and Cl adsorbing on different metal surfaces with different ligand metals in the subsurface. And just using domain intuition, we looked at other features, but we narrowed it down to just a small subset of features that we probed with this IGAM analysis. And I'm just going to show you some main highlights, specifically strain and the number of d electrons. So here I show you a feature shape for platinum alloys for oxygen adsorbate on the, should have probably been using this laser pointer here for a long time. So this is showing you the strain versus the change in binding energy. The orange line is the IGAM prediction, the black dashed lines are the confidence intervals. It has this discrete shape because it's a decision tree, so that's the shape it will always take. So you get stronger adsorption when you have more tensile strain. That's true for O, that's true for OH, that's true for S, that's true for chloride. It's true for every material we looked at. It's not just true for platinum alloys, it's true for rhodium, palladium, etc. It's very general. And again, it's when these surfaces feel tensile strain, they're going to feel less coordinated. They're going to want to bind things more strongly. What was more surprising that came out of this analysis was that you can just look at the change in ligand d electrons and basically just count electrons, and this tells you a lot depending on the host metal you have. So here I show you a feature shape for O and S adsorbed on different platinum alloys. So this is the reference to platinum. So 0 would be that the ligand metal is platinum. So if you have a noble ligand metal, if it's becoming more noble, then oxygen and sulfur will bind more strongly. And we thought, oh, that seems like it would make sense, because if the ligand metal is more noble, it's going to interact more weakly with the surface. The surface will feel less coordinated, so it's going to want to bind things more strongly. But then when you look at OH and Cl, you get the opposite trend. So this comes seamlessly out of this feature shape. So expanding this to a few more metals, here's for rhodium and iridium, showing you 4 adsorbates, sulfur, oxygen, Cl, OH on the rhodium surface, which is D8, and also iridium. In all cases, you get stronger adsorption as the ligand metal becomes more noble, as you perturb it in that direction. In contrast, for D9 metals like palladium and platinum, you have some that behave, that get bind more strongly, and some that bind more weakly. And in the analysis, you can deduce that for covalently bound adsorbates like O and S, it's going to bind more strongly, and for more electronegative adsorbates like OH and Cl on these D9 metals, it's more dominated by polyrepulsion, so it's going to bind more weakly. So that comes out of the feature shape. And then for silver and gold, which are noble metals, it doesn't matter which adsorbate you have, they all will bind more weakly as the ligand metal becomes more noble because of increasing polyrepulsion. So basically, if you know what host metal you have and you know what ligand metal you have underneath, depending on how noble that host metal is and how electronegative your adsorbate is, you would have a good intuitive understanding of how the adsorption strength would be perturbed. And using these analytical models and physics models are useful, but this also comes pretty seamlessly out of this type of analysis. So I hope IGAM had identified this ligand effect and strain effect. The most important effects were the strain, the number of d electrons, and also the size of the ligand atom, which I didn't have time to talk about. Interpol machine learning is a clearly powerful tool. I wanted to shout out this paper from Han Liang and John Kitchen and collaborators, where it shows that these type of approaches can have a lot of merit and could continue to be used to find insights. So they looked at theory-infused deep neural net to net and did Shapley analysis on similar data. And they found that orbital resonance and d-electron hopping was very important. This has to do with energy misalignment between orbitals. So this Shapley, basically the takeaway here is, I think here's a distribution of data, distribution of Shapley values. This is the average Shapley value. So charge transfer was not important, and I believe there's spectroscopic evidence for this being true also, so that makes sense. Strain and ligand effects were quite important similarly, but then this resonance effect, which has been largely overlooked, was also very important. So I believe that these types of methods can be used for other types of catalysis problems, other types of systems. Just to segue into that, we will have some opportunity in the challenges discussion. I think integrating with experimental data would be very useful, but we all have discussed this morning how there's some challenges with that. And I'd love to hear more about that in the future discussions with you all. We also heard about the improving model accessibility and reusability, not making these just one and done models, but somehow making them useful for people that do experiments and making them easier to use for everyone and reusable. Just for those who are less experienced in this field, I thought that, I wanted to note some issues about, explaining ML interpretations is always going to be a challenge. We have to use our domain intuition, like we have to use our catalysis expertise. It's never going to explain everything for you, in my opinion. And one caution is remove correlated features. A lot of studies, I think, have features that are pretty correlated, and that can make interpretation challenging when you have lots of things that are correlated with each other. We need to always remember that correlation is not causation, and there could be hidden confounders. And I think there's opportunity to collaborate more with causal experts, or experts in causality, and seeing if that could help advance these methods in catalysis. And also, we need to keep in mind that often we still have small data sets, and if you change your train test split, if you have a small perturbation to your data set, or a change in your features, you can get different feature importance scores, rankings. You can get nearly degenerate models that have similar, the features might be different, but they might have similar, RMSEs or MAEs on your test set. So we have to keep those things in mind when we do our interpretations. So with that, I'd be happy to answer any questions for the remaining minute, or if there's time.
Any questions?
And thanks for this talk. In the generalized additive model, where you have linear combination of one variable, can you talk about what happens if you have a feature that really should be like x times y, but you have a model that's x plus y? Where does that non-linearity come from in those shapes?
Yeah, well, ensemble of decision trees for each one of these, but also I didn't talk about it, but you can include pairwise interactions. So you could have f of x1 comma x2, and then you have these contour maps where you see how changing x1 and x2 impact y. They're just pretty difficult to explain, but they're there also if you want to include them.
Any other questions? Maybe I'll help. So this is really interesting to see how we can use the domain knowledge to actually impose the model. But what's your opinion about this type of human bias? We don't really want to have too much bias that sort of prevent you to start new knowledge. So what's the balance there?
I think, I mean, these models are quick, easy to train, so you could try many different combinations of features and build many models and then distill them down. But yeah, I think you should try to be unbiased and also try different combinations. And if you discover something new, then you should be open to that. I don't know how to, you could also add that as a constraint in your model to try to enforce it to learn from the data and not from, any biases. Like there's this I method, expert yield estimates, kind of like lasso, but yeah, it's a good question and something that we have to keep in mind. When we do interpretations, people can often interpret what they want to see.
So Randall can come set it up. Do we have other questions? Maybe you're ready.
Yeah, related to the symbolic recursions, I kind of like them. So I want to hear your opinion. You were a little bit.
I'm not against it. I've used it. I think that it has a lot of promise. I just think that for some problems, when you apply symbolic regression, you might get one solution that's so much better than all the others. It seems obvious that you should select that model. But for some problems, you might have 50 models that all do almost similarly, but the features are changing. And then it's how you pick one of those 50 models and then start to interpret it. That was my.
Maybe because the features have not been known or, look for dependencies before.
Potentially, but there's also, again, I like this method CISO, but it creates a feature space of billions of features. And then it down selects and it generates many millions of models. And that naturally, if you don't have a lot of data, there could be a lot of different ways to fit it. Even if you say, make it a one-dimensional model, two-dimensional model, there's still gonna be 10 models that can do it. So I just think that's something that has to be, at least people should be aware of. So basically instability in these analytical solutions.